Kia ora, hello everybody in Year 12 Physics. And I'm including my class plus Mr. Kumar's two Year 12 Physics classes too. A really tricky question which has thrown some focus, question 8 on page 89 of the workbook. And that looks like that. It's a bit wrinkly because I just took a photograph and dropped it in. You might recognize that. The first thing that we have to do, and I might even just give myself little pretend laser pointer here. There we go. First thing we have to do is position the suspension cord so it's 0.1 meter from here, and then figure how far along this 3 newtons. The 3 newtons middle toy has to be slid. Well, if we slide along, make a little pull out the little bit that we really need. The middle toy suspended from the slid along from the middle here, and this suspension cord is 0.1 of a meter. What I've done is, first of all, I've drawn in the weight of the bar, which I'm going to deal with very shortly. So the question states that the mass of the bar, the rod, is 0.11 kgs. I don't want to have separate masses and forces, so the weight of it is WMG. W is mg. Putting in those numbers, 0.11 kgs times 9.8 newtons per kilogram gives us 1.078 newtons acting down through the middle. So then I can get rid of the bar by just replacing it with the force vector, which is easier. Now this is acting down through the center of the rod. In other words, a distance of 0.15 meters from here. I've not drawn it on, but I'll be talking about it. 0.15 meters from here. If we find the torques or take moments about the suspension point, just here, we get the clockwise torque will be this blue arrow force, the weight of the bar, times its distance, plus 3 newtons times its distance, plus 1 newton times its distance. Now we have 1.078 as the weight of the bar, times this distance here in between the weight and the bar. It's 0.3 long, half of it from the middle, I haven't drawn it very well, sorry, is 0.15, that's 0.1, so that there is 0.05 meters, and I've written that there. This one here is the clockwise torque is this weight force, 3 newtons times its distance, and we don't know it. The book suggests X, I'm happy to live with that. Plus this weight, 1 newton, times this distance, that's 0.2, because if that's 0.1 and the whole thing is 0.3, we get that. Now, next step, if we squeeze all that up, we get 3x, put that there, and 1.078 times 0.05 is, I think, 0.0539. Add on 1 times 0.2, get 0.2, and we get this is the clockwise torque. Then we add in the anti-clockwise torque. Well, that's a bit simpler. It's this 5.8 newtons times this distance, 0.1 meter, which gives us 0.58 newton meters. So if we just pull out the handy information from this page, we have the clockwise torque is this thing I covered before, and the anti-clockwise torque is 0.58. The thing is in equilibrium. It's not tipping this way or that. So the clockwise torque is equal to the anti-clockwise torque. So there we can say 3x plus this thing is equal to that thing. If I subtract this thing from both sides, it disappears from here and this thing gets smaller. So 3x is 0.3261. Play with your calculator, check it please. Divide both sides of the equal sign by 3 and we get x. Now if we go back a bit, in primary school the equal sign means this question is going to give us this answer over here. In high school, it means this thing here is going to be the same as this thing here, like a balance. If we change one, we have to change the other. So I'm taking 0.5239 off this, take 0.2539 off that, and we get that. Divide both sides by 3 to keep the equal sign okay. We get that. Or x is 0.11 meters or 110 millimeters. To 2 significant figures, and this is the answer that the book gives us in the marking and the answer schedule. Cool. For the second part, the 3 Newton weight is slid to the middle and it joins the weight of the wire. Now, instead of having 2 separate vectors acting in the same place, I'm going to add these 2 weight vectors together to give me 4.078 newtons acting straight down through the middle. That's really handy. Second thing, the book takes moments, finds talks about the suspension point, and that works. It's not the easiest way in my view. So what I will do is I'll work through the book's method so you can see what happens in the back of the book, and then I'll use one of my own which I believe is a bit simpler. So as per the book, the anti-clockwise torque, which is going to give us this rotation, the anti-clockwise torque is going to give us this rotation, which will be this weight force times this distance to try and turn it that way. Cool. And that distance is x, whatever it is. Now, clockwise torque, well, we've got those things actually. It's going to be equal to this weight force times this distance, which is 4.078 times. Now, the middle to one end is 0.15. That's x. That's 0.15. This little bit here should be 0.15 minus x. Cool. Written it down. 4.078 times 0.15 minus x. Neat. Then we add on the effect of this thing. 1 Newton acting at this whole distance. This thing is 0.3. So therefore this bit here, where from the pivot out to the 1 Newton weight, is 0.3 minus x. Neat. Now if I just multiply out the things that we've got there, 4.078 times 0.15 is 0.6117 minus 4.078x. Then we add on 0.3, 1 Newton times 1 times 0.3. Then we subtract 1 times x. We can make that a bit simpler, because what I've done is I've added the 0.3 to this 0.6117 to get 0.9117, and minus 4.078x minus another x is going to give us minus 5.078x, and so therefore that's the clockwise torque. We have equilibrium, so therefore the anti-clockwise torque is equal to the clockwise torque. So 5.8 times x is equal to the thing we just said over here. Now I'm going to add 5.078x to both sides. That makes minus 5.078 plus 5.078. It's gone from the side, and we make this one a bit over 10.878. And therefore the number here. Cool. That means we've now got just a straight multiplier. We're gradually getting rid of the clutter around the x. Now x has been multiplied by 10 point whatever. If we divide both sides by 10 point whatever, we're going to get the x thing. So I've done that. If we divide that side by it, it's gone. Divide this side by that, there it is. And so therefore x is 0.0838 meters, which the book rounds to 0.084. Cool. Neat. Moving along. Alternatively, this is how I prefer to do it when I worked at it. I use force up equals force down. It's one of the two conditions for equilibrium to find the tension force. That's a good first step. So tension force is equal to all the downwards forces. 5.8 plus 4.078 plus 1. Upwards tension is 10.878. Then I want to take moments about the left-hand end. If the whole thing's in equilibrium, the torques balance about everywhere, no matter where you choose. And I'm going to choose a pivot point about this end here. And I'll show you why shortly. Now, the clockwise torque is going to be equal to, clockwise torque? Oh yes, there's the pivot there. It's going to be equal to all of the forces times the distance. Right, there's the pivot. I'll just draw a little pretend triangle there. Pivot. It's going to be this force times its distance, which is 0, so that's fine, plus this force times its distance, so that's 4.078 times 0.15, plus this force times its distance, and that distance is 0.3. We can
multiply those out and we get the clockwise torque, and you can check that with a calculator. 0.9117. Anti-clockwise, the tension force, bear in mind there's a pivot here. The tension force here, if this is a pivot, is trying to tip the whole thing that way anti-clockwise. So it's tension times x. Now we know the tension is 10.878x. For equilibrium, no matter where we measure the torques, let's do it, anti-clockwise torque is equal to the clockwise torque, which is kind of cool. And so then we have 10.878x is equal to 0.9117. Divide both sides by 10.878. In fact, it's the same equation as before. And we get x is 0.084 as before. And there's my little marker to tell me it's my last slide. Thank you very much, everybody. I hope this little video has been useful to you. And I'll be posting this very shortly. You'll see it there.